thank you. A few mentions about what happened recently. So machines in general, like robots, humanoid robots or cars, they've become better and better in understanding the real world, navigating the real world, navigating obstacles. Then, of course, we can't have a symposium on AI within these couple of weeks without mentioning ChatGPT. So it's not just about computer vision, understanding the real world, understanding to navigate the real world. Machines have also become much better at making sense of language, using, for example, natural language processing to understand how a user plans to perform certain interactions. Now, in augmented reality, we actually have a big advantage when it comes to letting our augmented reality application understand the real world. And that is because we don't just have a single sensor, we don't just have only a camera or we have only text, but we have a whole multitude of sensors that will allow us to better make sense of the real world. Just to give you an example, one of these headsets, we have, besides the RGB camera, which is sort of the standard for computer vision, we also have a depth camera. We have multiple head tracking cameras on the side that I, for example, use together with the IMU for SLAM. We have eye tracking, so we can understand where the user is looking at. We can have hand tracking, which is then usually based on the depth camera data, hand tracking to better understand what the user is interacting with. We also have audio. So when it comes to the medical field, audio very relevant. Lots of medical training right now is done via verbalization, where we say, like, what tasks are we currently doing? So audio could also be very relevant to provide information what the user is currently doing. Here are some examples. What could this type of context aware look like? And these are actually from quite old, but very nice example videos of how AR can change our world and how this context awareness can have an influence. So on the left is most of it, this video by Keiichi Matsuda, the hyper-reality video, is most of a dystopian example. It is like somebody walking through the aisle in a supermarket. It's so almost like every producer and every section shouting at you to buy it. But it could be also more useful applications. Here in this video, which is called Metaverse, and it is published by Metaverse in YouTube, I think already over 10 years ago. And they show in this example, for example, how we help somebody with cooking instructions. However, the context awareness, of course, can be also very, very relevant for medicine. So in medicines, we might have different tasks, we have different procedures. Depending on the patient and the state of the patient, we want to know different information. So the context awareness becomes very, very relevant for the medical field as well. And that is why today we have invited Doughty from Intuitive Surgical and Karthik Ramani from Purdue to discuss this topic. Just a very short introduction. So Karthik is a Donald W. Featherson Distinguished Professor of the School of Medical Engineering at Purdue University. And now for the people who don't know yet, very important with this symposium, Karthik is basically coming back to his roots because he did his PhD at Stanford University in 1991 in mechanical engineering. And then he was also visiting professor in computer sciences in 2008. Karthik received many awards from the National Science Foundation and other organizations. He has been on the editorial board of the Elsevier Journal of Computer-Aided Design and the ASME Journal of Mechanical Design. He serves as the Engineering Advisor Subcommittee for SPR-STTR for the NSF. In 2006 and 2007, he won the Most Cited Journal Paper Award from CAT and the Research Excellence Award in the College of Engineering at Purdue. And in 2009, he won the Outstanding Commercialization Award from Purdue University. He was also the co-founder of the world's first commercial shade-based parts search engine, VisSeek, and more recently co-founded Zero UI, whose product won the Best of Consumer Electronics Show finalists, so the CES 2016. And also, one thing to mention, so if you look at the website of the Convergent Design Lab at Purdue University, it's a beautiful source where you see multiple papers, videos, and applications, how to create content in AR. I'm sure Karthik will talk about that and make you check out this website afterwards as well to really see like what nice inspirations and applications there are. And now Mitch did his PhD in medical biophysics at the University of Toronto, where he was working under Dr. Nilesh Gugre as part of the cardiovascular MRI research group at Sunnybrook Research Institute. Currently, Mitch is now working as a research engineer in the AR/VR group at Intuitive Surgical, where he's developing novel applications for extended reality display systems like AR and VR, of course, with the focus on medical applications. Now, Mitch is a great candidate for this panel because he has been extensively working on mixed reality applications that utilize multiple sensor streams of the AR headsets, including the RGB camera, but also the depth camera, to make sense of the real world, and has, during his PhD, developed a novel surgical guidance system that relies on computer vision to recognize different tasks during a surgical procedure. So now I would like to give the word to our panelists. And then I think we'll start with Karthik. If you can, I'll stop sharing my screen. If you can, please share screen and go ahead. Thank you very much.
Yeah, thank you, Christoph, and also Lily for putting all the work behind organizing this panel. Timing is great and appropriate, and also for Mitch to participate here. So can you see the screen? Can you hear me?
Perfect.
Right, great. All right, we'll get started here. Yeah, so so I have some rights to put the Stanford logo here. Curiously, Stanford started in 1891, and I graduated in 91, so it was centennial year, and big bragging rights for being the centennial, and it's so many years after that now. So yeah, augmentation is not new. In fact, it has its root back at the Stanford campus. I'm sure all of you know Doug Engelbart, and in 1968, of course, he brought this thing out called the mouse and the WYSIWYG and the hyperlinks, and he was thinking of the entire ecosystem rather than just a device. But more than that, he also built AR headset that not many people know. So the point here is, as Mitch mentioned, historically, that computers have not been a part of our body, aiming out from our eyes, and also be able to potentially understand context, as well as our viewpoint in identifying context from moment to moment at that level. So with that, I'm going to not talk about all these currently available headsets or things you can buy even in an airport. But our main point here, the central vision for our lab and its appropriateness to this nice workshop and thinking Christoph has brought in, is that it's about augmenting human, and more importantly, by blending digital and physical, especially designed around and for human experiences, and in a human-centered way, which means, you think of a future that is possible, bring in the constraints there, understand the context, and design towards that future. It's kind of easy to say, but oftentimes harder to do. So this is our Intuitive's room, and the perspective that I want to bring in very quickly in just 9 to 10 minutes is authoring, number one. Number two is understanding. And third is interacting with those environments, and in particular by blending in what is possible in mixed reality settings, the technology enablers, but centered around the human, and also bringing in AI in terms of using AI in real time. That's kind of, you'll see all the apps that I'm going to be showcasing here coming either from computer vision side or from HCI side. And more importantly, these communities are further apart, even academia, and our lab bridges that gap very, very strongly. And so the future of surgery. Hopefully, the panel discussion will center around this and how we can develop the MMR of the future. So authoring in AR context. So first thing is the authoring journey in AR, if you want to do one, is pretty hard, let alone all the other issues. But in general, besides the hardware and connectivity and so on, which is going to happen in the future, it takes a long time. And you need experts. You need experts in Unity and or coding. And if you want to go further, modifying stuff, and you get stuff which you can't even edit at the end of the day or change it. End users can't really develop AR applications. And if you look at YouTube and others, a company will probably need thousands. And per minute, just look at the countless number of YouTube videos created. So if you want to envision a future where AR is more pervasive, we have to address the authoring problem and enable authoring, which is the creation of applications without having that much technical expertise. So the current way in which stuff is done is not sustainable. That's my main point. And to that, the first illustration here is Capture. And Capture was presented at WIS 2020. You can go to our website. I put it in the chat, but you get a better view. But basically recognizing that human behavior plays a very important role in what we call context-aware applications and how we can build them. So the idea is to first author. So a novice can author and say that, okay, well, I'm doing this activity. I'm opening a book up. If I read a book for half an hour, after that, remind me to do some exercise, right? Something like that. So all these workflows, we want to enable anybody to be able to author. And so you want to be able to recognize the context and then create it. And we use these metaphors called trigger action programming, but essentially building that layer of intelligence to enable such apps. So for instance, as I show in this illustration, I'll show you a short video. There's a tea kettle, there's a cup, and you're creating a reminder for eating pills. These are the types of use cases that we developed and tested in a virtual environment. So very short view of Capture. So these will be very short videos, pardon me, given our time. So the idea is, as I mentioned, at that time when we developed the Oculus didn't have down-facing, so we developed all of the extra hardware and we put a laptop on the backpack. We needed more real-time processing and AI use. So he's actually, the user is actually creating and replaying with an avatar that if I do this, do this. And so the logic behind what has to happen has been created on by the user. And when coming back into the real world and he's using it, it can trigger sensors or IoT around and make the application work. The second one is processor. This is more procedural. I think it has a lot of relevance to surgical procedures. But basically, the idea here in procedure is that delivering spatial information for training in workers in this case is difficult. And again, here, the theme is authoring. So we wanted to experiment and develop in creating procedural instructions and for instance, embedding 3D, embedding 2D videos and so on from the point of view of how you want it created and in the way that you want it triggered. For instance, in here, we also had visual identification of targets, and potentially if the number of tools are not the right tools or using the wrong tool at the wrong time, it won't allow you to go to the next step, number one. Number two is it also verifies that you're doing the right thing. And the main idea here was for the author to create such applications. So use the real tools and you author with real tools, and it uses visual search to search and identify the tools and superposes them on the virtual ones. So you'll see a view of processor.
All with a simple press of a button. Proceed to demonstrate the task.
So the idea of processor, as you can see here, all the virtual parts appear on top of the physical one, and you perform the procedure. So that's the authoring mode. And in the use mode, it'll ensure that the nature of how you want it to be used is satisfied. So next, I'm going to move to Edit AR. Edit AR is kind of a even more different twist from processor. In Edit AR, you just do a demo in augmented reality, and it creates the virtual reality and augmented reality instructions and the video all from the AR authoring environment. So there's a complete digital twin just arises from the demonstration. So I'll show you a little bit of it. But the interesting thing here and in processor, you'll see that creating these procedural instructions and embedding content is not only better for the user as shown by a lot of the user studies and so on and so forth, but also it's much, much faster. For instance, here, it's almost like 5 times faster than creating other video-based instructions, right? And better as well in terms of the learning gains and potential additional things that you could do because it's embodied. It's all related to skilling and using your body, using your hands, and trying it and doing it. But also, you'll see here, in the AR authoring mode here for repair of a bicycle, for instance, right? The steps that you want somebody to follow, and it'll trigger the instructions for the next step based on the previous one, but also it creates a VR. And the video, you can change the camera to any location once you create it. So you have a virtual 3D content, and you can create video based on the AR instructions for more extensive distribution if people don't have headsets and so on and so forth. So that was the idea behind Edit AR. All of them use avatars, and we have done a lot of work with avatars and using those avatars for procedural instructions. So understanding is adapting AR using AI, of course, with hand-body tools and with the environment. There's a lot of work that we have done in this area, predating even Kinect and so on and so forth. I'm not going to go through this, but a series of computer vision papers in CVPR and so on and so forth. But some of our early work that created robust representations of hands used this recommender system. And the idea is very similar to the Netflix algorithm. It recommends the nearby hand poses, works quite fast. At the time we implemented it at 30 hertz, just enough for us to replicate the hand and pose. And it reduces the search and then imputes the geometry for the hand, and you get the hand by some magical transformation and matrices, and this can be made to work in real time. But what is more important is our current use of this in gesture AR, which is a UST 2021 paper. We created frameworks, design guidelines for using AR don't exist. So static promoting, like discrete gestures, and you hold a hand, and then continuous gestures, like manipulating this mug. The mug, of course, can be created instantaneously by scanning. And then, in this case, hand pose changing, and you want some dynamic effects out of discrete actions, right? Like the Coke can just vanishes. And more interestingly here, they are response to the user's gestures. So such types of trigger action programming and or use in AR is all possible today. And as you might guess, the AI is operating real time in the AR, and the input-output mapping happens dynamically. I'm going to quickly not go through the equations here, but more recently, our lab currently is on the leaderboard for activity recognition in CVPR across several data sets that are present. I'm pretty sure somebody's already gone past it. But more importantly, what we have done here is for similar types of actions, oftentimes, you get one of our reasons that our team, Hyungun, and the team were able to surpass a lot of the current data spaces was a self-attention-based graph convolution algorithm, which uses the intrinsic topology. So for instance, when you're moving your hands and clapping versus waving and pointing, you'll see that there are small lines that go from the hand to the leg and various other joints, right? And some of them are dark, showing stronger relationships for those types of activities. And using such kind of algorithms, it's very possible now to almost anticipate what the user is going to do in the next 30 seconds or a minute and so on and so forth at the task level. I'm sure this has relevance to surgery. I'm going to switch. Now, what do you do with these types of recognition algorithms and so on? So bringing that computer vision now into adaptation, here is a tutorial where the AR actually understands the user state, understands the machine state or the environment state, and makes an adaptation decision as to how well are you doing? Do you need help? And I'm sure even in surgery, depending on how expert a surgeon is not, you schedule more or schedule less. And you can see that in their confidence in the hand wavering and so on and so forth, right? I have seen some videos shown by somebody who has done some work here. And therefore, I am making this guess that such algorithms are going to be very useful in SMMR. So I'm going to sort of show you how this is done. But the basic idea is the authoring mode. So here, using a laser cutter, for example, there's adjustment of the laser, the part, and then an adaptation decision based on how confident the user is. So it's, the AR is continuously monitoring the user activity with the environment and making the decision. So we have different levels of detail of help. So if the user is fairly confident in doing stuff pretty well, you don't need anything. Otherwise, we go to the subtask and give a description or expectation of a subtask, for instance, and basically we use the avatar, the animation, expectation of the user, and the subtask to allow the user to get more help, or the AR gives more or less help to the user, and shows animated components for a step of a subtask, for instance. And this is done based on some kind of a decision model with a CNN, and it allows and it looks at how the user is paying attention to the targets. So quick view of this. It's an expert records a machine task tutorial step by step in AR, and then the adaptation modality understands the real-time status of the user when he is using the machine, and then the tutorial elements adaptively changes based on the expectation of the user, or how well the user is doing in terms of the various tasks. So this level of detail help, all of that happens in real time to guide the user. Okay, so the last part is interacting, right? Handling, performing operations, and the multimodal interactions. This is a cool paper. Definitely worth watching the video on our website, and if you have time, read more. But the idea here is 6DoF estimation of objects has been a very pervasive problem in computer vision. Even we have been working on that on the other side. Here's a very creative solution put by our team, Shun and Femming and others, where they actually inverted the idea. So here we use the HCI to solve the AI problem, because AI is still struggling in a lot of these occlusion issues and so on. So what we do is we found that creating these data sets across all things, and AI tries to overgeneralize stuff, whereas for context-specific applications, you're not going to use a million tools or things like that. It's very possible for the end users to train to their specific tool. But then the question is, how do you uncouple the hand and object and do the training? So the trick here, that the key idea here was, we just inverted the idea. So basically what you do is you create an outline around the object for better accuracy for labeling in AI, and then you just record with the object and the hand, but you don't use that for training. Then you take the virtual object, and the system guides you as to where to hold it and move, and all the training procedures that the AI expects from you. You just move the virtual object, so it's not unaffected by the hand, and the training becomes really good. And then you're done. So essentially what you have is you have trained it with the hand, and now the CNN has learned the object and the hand simultaneously. So that's the label recording. And then this is the recording with the labels. So it just inverts the object, and this is a real-time use by the AI. And this is a problem that AI is still struggling to solve. And now, of course, we tested it on various types of objects and so on and so forth. But for more contextualized and custom data sets, that brings a very powerful method for end users to train very quickly and put things to use, the physical objects. I'm kind of moving into like more physical haptic experiences, but in VR. So you're actually, in this case, we reversed the learning goals and created training content for welding. And just to give you a feel for what we did here, you're actually using a real gun, and actually it's also creating the weld beads and so on, which is very much simulating the welding conditions. And we actually have deployed this for training. There are several other applications that we have been working on since then with industry. Unfortunately, I can't share all of them because of NDAs. But in general, the main idea is that the training can happen in very realistic environments in VR, and also blending of VR and AR is possible. And we have done a lot of user studies in maintenance and procedural activities, etc., where we target the application to specific learning goals and causalities, so the learning gains go better. So it's a more systematic method for authoring in VR or in AR to increase the engagement as well as the learning. So MEC-AR is again, the sensor-based environments, the tools, the robots, the environment, a lot of it in MMR can be sensorized in the future as well. So the idea is, how do you author in AR? Rather than take a toy and just play with it, AR can augment it, which people are doing, but then the end users can't create such augmentation. So how can you create bidirectional, meaning from the physical to the AR, and then from the AR into the physical in real time? How do you create such interactions? How can end users create and author such interactions? That's a question that we went after here. So the sensing and actuation modules, we embedded in the toys, and then we created a bidirectional toy AR interaction program environment. So for instance, you open the toy box and then you want the ghost to be animated, right? Coming out of the box, but it should move and increase in size proportional to the movement of the lid. So the same sort of programming modalities that you saw in the very beginning comes here, but now we have an entire set of sensor kits, haptic modules, and so on and so forth, which can be used to modify the toys. And then, visual effects in AR and so on can just be dropped in, and then they are all enabled when you do the physical interactions. So it's a pretty fun project, sort of motivated after a toy design class that I developed here in the 90s, and it's become quite popular on campus. Okay. And last is the robot AR. Robot AR is a mobile robot operated remotely and on the cloud. And so users can interact with the robot to go around a student, for example, in a remote environment. But also the interesting thing about this is, for a lot of the questions that the user asks, there's some NLP kind of capabilities here that users can not only interact, but also they can ask questions. The real instructor only has to come in when the answers can't be given by the system, which is perhaps like 30-70% are fairly standard stuff that get answered. So that's it. And wanted to thank all my students, without whom I wouldn't be here, the sponsors, NSF DARPA. Thank you so much.
Perfect. Thank you very much. Yeah, wonderful. Plenty of resources when it comes to the different fields, the interaction and the understanding. And now we would like to switch to Mitch. One note to the audience. So if you have questions after the 1 hour, we also have a short interactive session in gather.town where you can then ask directly to the speakers. Also, if you have some very pressing questions, please put them in the chat. We'll try to address some of them during the end of the panel discussion. Mitch, please go ahead.
Awesome. Thanks a lot, Christoph. And thank you, Karthik, for that detailed introduction. I think there's a lot of opportunities, especially something that sounded really interesting to explore in the medical space would be that idea of adaptive training, being able to cater a learning experience to respond to the kind of skill and knowledge and experience of the user in order to improve their training experience. So potentially some areas for collaboration in the future. But yeah, I'd like to thank Christoph and Lily for inviting me to be a part of this seminar. So I'm going to talk a little bit about Intuitive as a company and what we're doing in the context-aware space, and then kind of focus on talking a little bit about some of my PhD work, just motivating the problem and need for context-aware surgery, as well as discussing how we can make these augmented reality applications more intelligent. So a little bit of background on Da Vinci surgery. Our main surgical platform at Intuitive is our multi-port XI system. And this system is, it's a fantastic surgical system. And I think there's sort of 3 core areas that Intuitive focuses on in terms of enhancing surgeon capabilities. A lot of these are relevant to our discussion here today. So first off is quality of visualization. And by this, I mean the high resolution immersive 3D display that Intuitive provides at our surgeon console. It's actually interesting to think of. This surgeon's console is actually one of the first commercially available, widely used medical VR displays. So this, in a sense, is teleporting a user or immersing a user inside of the patient and providing them a view of that stereo endoscope data and allowing them to operate at a high level of visual fidelity. Second to that is understanding the relative orientation of the person or surgeon to the task. And this is introduced through our intuitive grounded hand controllers that also have a number of other smoothing and tremor filtering techniques incorporated. The idea here is that a user's inputs are very clearly mapped into movement patterns or control of the actuated robotic instruments. So being able to perform wristed movements and have your inputs very clearly map into your visual and motor controlled space. Finally, and I think most relevant to what we'll be talking about today, is displaying information to a surgeon or physician as it's required. We've done a lot of work with our IRIS program for the generation of preoperative 3D virtual models, making these models available to a surgeon during a procedure whereby they're able to adaptively control the appearance and presentation of these models to be optimal for whatever surgical task they're performing and improve that procedure. So just asking a question in the sort of medical sense, what does it mean to be context aware? And context awareness is sort of a very broad field, but the general idea is we're trying to provide the ability to a system to understand the circumstances and environment in which it's being used. And I think one context-aware application that we're all familiar with are weather alerts. So if you search the weather on your phone, typically you'll be prompted whether you want to allow Google to use your location. That GPS location is then used as a contextual cue to provide you with specific data rather than requiring you to search a preset location. Specific to intuitive, one of the sort of context-aware applications that a lot of people don't think about is in our XI instrument control. So when a user sits at the surgeon console and places their head into this VR console, there are sensors on the side of that console that detect the head-in event as a contextual cue. That is then being used to say that, hey, there's someone sitting at the surgeon console who likely would like to operate. After this detection event occurs, the surgeon is then prompted to match the hand controllers to the current instrument pose. After that matching has occurred, the surgeon's then able to take control of those instruments and begin the procedure. Another opportunity or use case, rather, of context awareness in Intuitive's platforms is with our newer ion navigation platform for diagnostic lung biopsy. And this is just sort of a small demonstration here, but the idea is that as you're driving to a lung site, a lung biopsy site, the proximity or distance to your target biopsy site will motivate some of the visualization information that's shown to a user. So as you go from this primary navigation task to sort of nearing your biopsy target, you'll see a fade through in transparency here, as well as a number of other visual cues and information that helps support the transition from driving to performing this biopsy task. So I'd like to just present a bit of background on some of the research trends in medical XR. And I was happy to see that Karthik mentioned the first head-mounted display. I think this is the same one that we're talking about back in 1965. This is actually on display at the Computer History Museum in Mountain View, so I definitely recommend you check it out if you're around. And a lot of folks, though, think that head-mounted displays and AR and VR in general is a very new field. Of course, this isn't the case, with many of these being invented in the 60s, late 70s, early 80s for sort of first applications. And this image in figure B here is very interesting. This is some work by Phil Green. I believe he was with SRI at the time. But the idea here was the design of this early telepresence surgery system that included a virtual reality head-mounted display and these data gloves that tracked your hand pose for use in controlling a surgical robot. And actually at the time, due to technical limitations and some ergonomics challenges, the latency, the image quality, and the update rate and fidelity of these gloves were found to be not sufficient for a surgical application, which is actually what went on and motivated the design of the intuitive surgical console, which I just think is very interesting. So looking at some recent growth in this space, this is from a review article that I published earlier this year. We've seen a lot of interest in optical see-through head-mounted displays in surgery. And again, this is from 2014 through to 2022, almost an exponential growth in the level of articles published and interest in this field. There's sort of generally been a focus into orthopedic and maxillofacial surgery across these articles, likely just due to the validity of the rigid structure assumption for registration. I think something that stands out to me as well is the reignition of this field in 2016 and 2017. That coincided with the release of the Microsoft HoloLens 1, which has been used in a number of applications since then. Some of the notable research findings in this area, spatial awareness, so benefits to complex 3D model or 3D anatomical understanding through providing a 3D display. There's been a lot of opportunities for improving mental mapping, so reducing the cognitive load of the surgeon in having to take 2D guidance information and project that into the 3D scene. We've also seen papers mentioning benefits in attention shift and ergonomics. So being able to create a virtual monitor, as shown in image B here, and place that at a position that is comfortable for a physician, and being able to move that and adaptively resize that throughout a procedure to their preference. So a little bit of background on my PhD contributions. The general focus of my thesis was on a head-mounted display-based augmented reality platform for image-guided media delivery to the heart. As we saw in the previous slide, there are lots of potential benefits or human factors that are addressed or partially addressed through the use of an optical see-through head-mounted display. However, what I also found was that there's a number of persistent human factors and technical challenges that remain. One of the most highly noted ones in this review article that I conducted was perception. And in this case, perception just refers to how a user interprets virtual content. So some of my early work looked into assessing perceptual accuracy in a targeted task. There was a study in a 2D model like this, and also in an animal model that I conducted, looking at how different perception locations or locations of virtual content affects a user's accuracy in a 2D or 3D task. A second problem in the literature that was commonly referenced is occlusion and risk of error. This can be due to loss of tracking during a surgical intervention, for example. So some of my work in a second project I investigated was into enabling markerless tracking. And it was interesting that Karthik was talking and mentioning about hand pose estimation as a potential feature for some of the authoring work. In this case, I used a joint understanding or representation of the rigid position and orientation of the surgical drill and a probabilistic model of the user's hand in order to improve the pose estimation for this task. Also, this markerless tracking is running on a HoloLens 2 through a low latency streaming approach where I'm sending data to a remote PC, processing and sending it back. My final project, and I think something that's most relevant to our discussion today, focused on addressing some of the challenges of context, ease of use, and interaction and workflow limitations that we very commonly see with augmented reality systems. So the idea here was using a head-mounted display. Can we record some information about the scene and then use that to adapt content to be relevant to what a user is doing? All of these things came together to form this augmented surgical guidance platform. So in the medical sense, I really see context-aware AR as an opportunity to improve workflow and some of these limitations that we're seeing with current guidance systems. On the left in image A here, this is just a user view from a study early on in my PhD work. And you can see that there's this user interface here with a number of UI elements. So what was required was that a surgeon would press all of these buttons to adapt the virtual 3D model to be relevant to the surgical task or action that they were performing. And here's just a video of me playing around with this interface, trying to adapt these models. So the idea for this project was through front-facing video on a head-mounted display, whether or not we could create a lightweight learning-based framework to learn about the tasks that a user would typically perform for a certain procedure, and then use that information to adapt the information that you're showing to them. This is kind of a debug mode that I'm showing here. This is just showing the prediction, probability, the inference time. And for this application, it was run directly on the HoloLens 2. So generally, I sort of see 3 different potential use cases for context-relevant AR. The first would be in guidance. So, for example, the predicted task could control the context, or sorry, choice and presentation rather of the augmented virtual content. So here you're trying to recognize the task that a user is performing and then meet their information needs. Second would be during training. So here you could use task prediction or interpretation of a user's skill to optimize content and enhance their learning. This could be through presenting additional visual cues, text or audio. And finally, we've seen a lot of interest in analytics. So being able to determine how much time was spent during portions of a procedure. However, there are many challenges that remain. Handedness of a surgeon, surgeon preference, so whether or not they want to use certain instruments or tools throughout a portion of a procedure, of course, experience, and then also timescales of prediction. So how do you detect short events? How do you then have a same network or prediction model that can handle long-term events? These are all open questions. So with that, I'll conclude my little presentation here and open it up to Christoph. Thanks.
Wonderful. Thank you very much. Yes, 2 super exciting presentations. And it was also very nice to show like the comparison first from Karthik, who also showed the non-medical use cases and where we also have a bit more experience how to, for example, interact with rigid bodies. And then you suddenly go into the patient where you have like the soft body tissue where things are always changing, are always different for every patient. Which then also leads to my first questions already. What technological challenges will arise from, for example, taking some of these models that we learned and that we have experience with from navigating or understanding sort of a more or less rigid real world to going into the patient, where things move around, where you mentioned some of the challenges itself. You might have a left hand or a right hand, and each individual case might differ for the patient. So, Karthik, yeah, if you perhaps want to start commenting on that.
Yeah, so clearly, I mean, stuff moves inside the body, and I think that's the biggest challenge, right? Like, also, perhaps Mitchen, you can comment more, but not the 3D endoscopes and so on that go into the body. Not too sure how good and reliable they are today, but that's an opportunity for research as well, the inside the body kind of procedures. But more importantly, in terms of a lot of these applications and their use, Mitch kind of talked about this debug mode. They have to be reliable and robust, and also the ability for us to depend on the modalities of AI, like many of which I was showing. So when it's in the training kind of an area, it's okay. You can get away when AR and VR are used for training modalities. But when it's real use, I think the level of reliability and so on has to be, so there has to be some kind of a backup, in my opinion, right? Like if it fails, what do you do, right? And over-reliance on some of these support and help and so on, this is something that I always think about. How much does it take away from your own thinking? Like, same thing like in driverless cars, right? Like, does it take away your skill when you put the sensors for parking, for instance, right? Or distance estimation and so on and so forth, that we have come to rely on, like nobody knows other people's numbers. I used to remember them in the past. So yeah, I think the memory thing, having it as an aid to enhance the human rather than humans becoming over-reliant and then not knowing how to fly the plane, which also is perhaps somewhat true these days with the newer pilots. So those are some key points that come to my mind. Maybe Mitch and you have other angles that I can build upon.
Sure. Yeah. Thanks a lot for that input there. So I think something when I first entered my PhD, I kind of thought that in a medical sense, if we could take these preoperative 3D models and directly superimpose them with minimal registration error onto a patient, that would be the perfect solution for a surgeon. It would reduce all the problems we're seeing with current image guidance platforms. Of course, that's not the case. There's a lot of other challenges in how surgeons perceive 3D models, how you present and render 3D content, how you optimize that content for the specific task they're performing, how you ensure that registration is maintained through deformation. So all sorts of challenges with that. I think something that motivated my interest in the context-aware field was that a lot of the prior literature in this space kind of focused on looking at either achieving clinical goals, like we were talking about reliability or usability, or engineering goals like performance and speed, those being our quantitative metrics. But those don't necessarily guarantee the transition of that work into a clinical sense. So sort of looking beyond that, what are the potential limitations of current technologies that are introducing these workflow challenges, whether it's through difficulty in setup that's sort of restricting adoption, difficulty in working through clunky UI interfaces, and that sort of thing. Specific to the idea of variation in data that we're sort of hinting at, I think this is true in all domains, but especially in a surgical context. There's a lot of variation in preference across individuals. So people use different tools, different entries, different surgical approaches, different handedness. There's also variation in skill and procedural knowledge level across these individuals. So different economy of motion, different time spent in different parts of the procedure. So there's a lot of variation that we're going to have to incorporate into our data sets in order to properly perform these sort of tasks and support surgeons on a personal level. Something that I think is also relevant that we haven't talked about is overall performance of these algorithms. So maybe less so for other applications, but depending on what it's used for in surgery, there's likely a high priority on real-time or near real-time performance. There's sort of two approaches that I explored for if you're using a learning-based approach to achieve that. One could be, as in the first project I presented, running a learning-based framework directly on a device. So in this case, you may have to make trade-offs in terms of network parameters or memory that's being used in order to run on a mobile device. So that could compromise overall accuracy and performance of that network, but it's much simpler from a hardware perspective. Whereas if you want to have a more sort of detailed model that requires more memory, may have better performance, you then require all of this additional bulky hardware. So you could make the case of whether or not wheeling in this cart and setting up this streaming protocol is going to be worth the trade-off in that case, as that's quite a disruption to clinical workflow.
Thank you very much, for the comment. So we talk now about a potential challenge for medicine, where things become higher risk potentially, where they might become a bit more difficult because of all these different variations and these different approaches from different surgeons. There might be also an advantage, however, like if we look at what types of data we can have to understand at what task a surgeon is doing, and thinking about Internet of Things, like the medical room, the surgery room is full of patient vitals and different devices that provide us information. How can that contribute to helping us understand what information is relevant right now? Mitch,
Sure, yeah.
you want to start?
Yeah, I can start. I think that's a great question, and a great point. So, of course, coming from Intuitive, I'm going to have to mention robot kinematics, robot event data as potential inputs to a context-aware system or contextual cues. We could potentially know, for example, what instrument is installed, the pose of our setup joints or relative positioning inside of a patient. Thinking beyond that, there's a number of other inertial sensors. So as we talked about with more modern head-mounted displays, you'll have a combination of your traditional computer vision sensors alongside an accelerometer, a gyroscope, other inertial sensors. In a medical sense, we could think of other patient monitoring or patient sensors like an ECG or anesthesia cart, potentially providing more information as to the patient's state. A couple other things that I've been thinking about specific to an R could be light or sound sensors. So if you're able to detect sort of in a traditional way, you would have video that you're recording to see that a surgical instrument is being used, but a lot of the time there'll be smoke or occlusion of that camera, so you may not be able to represent that event well. But if instead you were to have a sound sensor and you knew what a typical surgical drill sounded like, that is something that's able to kind of get around occlusion. You're able to have these redundant sensors for interpreting what's going on.
Thank you. Karthik.
Yeah, I can add to that. First, a little bit of a segue here. Hardware also in real-time performance, as you saw in a lot of our work for latency and so on, we actually put a very powerful computer in the backpack. And so I think that has to come up, and of course, the robustness. Now, transitioning to your current question, I think this opportunity is huge, and especially with someone like Intuitive in place that can change the OR experience, right? Like you have control over the hardware. Whereas in traditional robotics, right, like the robots don't talk to literally anything around because that manufacturer doesn't want to share their interfaces with the AR headset or with the HMD or with the conveyor. Everybody wants to play their own game. So from a commercial perspective, that has kept commercial robotics behind, in my opinion. It doesn't talk to the CNC machines and tools and even the humans, right? So whereas in robotic surgery, there is more incentive, and a larger company like Intuitive can drive the ecosystem in the room. To that end, so the awareness is key, right? Awareness of the humans, of each other, humans of the robot and the machine, and of the patient, and all things working in synchronicity, right? So that would be the North Star vision, if you may, where everything knows the status of other things. That said, right, I think a lot of other cues come from the surroundings and the vision. The vision being on the humans does solve some problems, but of course, occlusion is always there. So occlusion-aware settings, and we do have a paper coming out in ICRA. Hopefully, it'll be accepted. But in addressing this occlusion-aware in real-time kind of cases, it kind of uses at a very high level a sentence completion analogy, missing words and so on. So a lot of that has been addressed very well. So one of our students had this bright idea of using that for computer vision, and it's actually working pretty well. So these types of solutions will help in guessing and guesstimating what is to happen. But awareness, context, the so-called context awareness of each device of the other and of the stage in surgery, and the criticality of that operation, right? What's happening? I think all of this is going to enhance the experience. I think the next set of things that will likely happen, and Mitch can comment to it, my guesstimate is there'll be more data collection and more like control studies to just see performance improvement, what is happening and how. And I'm pretty sure with the robot, they can already collect such data across and compare different surgeons and different operations and procedures and expertise level and so on. So I think that probably already exists, but its ability to talk to the devices around, including the AR headsets, that is going to be an interesting challenge to see how that is overcome, whether that sharing and interface happens more seamlessly and the latency there. But it's a huge opportunity overall to change what's going on inside.
Thank you very much. I saw that there are many questions in the chat already. I also encourage you, like if you have specific questions, please ask them also directly in Gather Town. One question that directly relates to AR and what you just discussed with also AI and the different situations that we might encounter. We have different patients, we have different sizes of patients, we have male, female, different nationalities. How do we avoid bias in AI-based awareness for medical applications? Like if most of the data is now collected at Stanford, for example, or at Purdue, you might have a certain demographic where you have more data and then other demographics.
Yeah, I have a quick answer. Actually, there's a paper that addresses this, but not in a medical context, just published called Scalar in ACM Chi. There, what happens is we have a centralized, it was for a kitchen, right? We have a centralized kitchen virtual model, right? And everybody's individual models, and the big one is learning from across all the nodes. And to that end, the sharing has to happen. I think privacy issues will play a role here. For a kitchen, if I create a refrigerator and interaction modalities here, I'm happy to share with other people. People are now sharing a lot of their data across. So I think that to some extent can perhaps reduce the bias model. But humans are humans. I don't know how much you guys should comment on that. But in general, I think that is one way in which where it can be shared, but federated database area is growing in research quite well, where it's shared, but privacy is still maintained, right? So that I think, because the human is a common condition, I think people will be more willing to share in this case rather than in more other situations.
Thank you. Since it's already 10 o'clock, I want to follow up with one last question to both of you. How fast do you think the field develops? Where are we in 5 years? How well do our augmented reality headsets already understand what we are interacting with, at what stage we currently are? Mitch, if you want to start.
Yeah, definitely. So I think specific to surgery, there's going to be a lot of challenges as Bruce just had his question with sort of diversity of data set generation and collection. I think that factors in quite a bit to context-aware AI and AR. I think looking forward to the future, of course, I would love to see this technology being used in operating rooms everywhere. But I do think that there's a few questions that remain to be answered. As we've talked about so far, diversity of data sets. I think one thing also is comfort. So depending on how you're using your contextual cues, say if you're adapting virtual content to a user's action, there hasn't really been a whole lot of work, at least in the medical domain, as to whether or not physicians or surgeons like having that happen. So typically, kind of my understanding from other fields is that you don't want to be making vast changes to the virtual information that you're showing to a user. So how can we sort of update this information to be relevant to a task without distracting or making it an unpleasant experience if we're just changing data all the time as you're changing these tasks. So I think in that sense, there's a lot more research work to be done, but I'm very excited for where things are headed.
Yeah. Karthik?
Yeah, I think the next 5-10 years is great for research. I mean, the answer to your question would have been different if you asked me a year and a half before the downturn. Things have slowed down. Maybe in some ways, as an academic, I'm somewhat happier because I have a bigger running ground. But otherwise, these large companies just hire away all your top students, and they're doing the research inside, and don't give us that much of funding. So it's a joke, a serious joke. But on the other hand, medical applications, I have very high hope that this is going to be one of the pull for AR as one of the lead applications. So it's going to come down to the value that the future applications can generate in MMR, and conversion of that value into tangibles, which is always hard in AR applications. The number of industrial applications we are working with, they are a little bit more understanding and willing to take that jump, but they are initially putting it in training. They are not putting it in real-time use, right? So, but the training, if they gain confidence, I think in the near future, it will transition. So there'll be AR-based training and then AR-based real-time use, right? So we'll have to see. But there are a lot of applications in the real world that I see are not life-threatening, but the payback for those is not clear. So people are experimenting, which is exciting. The headsets are going to decide, and the competition there. I wish there were a more open academic AR headset that is out that we guys all play with and not depend on Microsoft and the Oculuses. That will be game changing, but the investments there are going to be high. I wish somebody, large team did that. That would be my first thing on the wish list to speed up the area. Perfect.
Thank you very much. So now also, everybody who knows our SMMR symposia knows we follow it by a short networking session in Gather Town, where you have the opportunity to directly interact with the panelists. So Patrick, Mega, Musamil, I'm sorry I have not yet addressed your questions, but you have the chance now in Gather Town. So Lily put the link in the chat. Then perhaps, Lily, you can also share the slide that shows the Gather Town. So please just click the link at the chat. You will automatically end up in Gather Town, very easy to navigate. And just make sure to mute yourself in Zoom or leave Zoom once you're in Gather Town, so we don't have any feedback. So then, if you have any questions, if the transition doesn't work, Lily will stay here for a few minutes.
Yes, hi everyone.
Help you out.
Thank you so much, Karthik and Mitch. I'll see you in Gather Town, but I will be, I'll stay in Zoom for anyone who has any questions on how to join. But thank you everyone for joining us.
Thanks so much, Lily, and thanks for the organization.
Thank you for coordinating, all of you guys.
Thank you. I'll see you
Thanks.
in Gather Town.